next one is that multi-purpose controller. This is like a CPU only, computer processor unit, and this is called as MPC, and each CCU is one MPC, individual MPCs, and so we have 6 MPCs for CCUs and one EICU, engine interface control unit, which is also using this MPC only. The block diagram of the MPC, this is the one, and it is having a set of input and output channels which can be programmed by the computer, and then it is connected with the network A and B. AB is for redundancy, they give 2 channels, and these MPCs normally this is showing like this a new MPC and having the channel list in the top of the MPC, and this is also channels. Plex, we called as a plex, and bottom board is the power filter board, and top one is that main input output board, and this is the daughter board, analog output and digital output board, and we have a battery here. This is for only clock running, and we can put it with the battery here. This is the new one, that is why it is there inside, and inside one CPU board is there, that is only actually operating here, and all the software is recorded there, processing there, and then when you are changing the battery, and this is the battery terminal, and this dongle terminal, this is one service connection, and this is for terminals like network connections, and this channels for analog outputs, and this is for main input output board, and these channels are named in the number wise. We have 4 pins in one channel, ABCD. A and D is for power supply, and between B and C is actually the signal input or output, which we can use any one like as per the program, and then these boards, it is layer by layer they set it. This is the power filter board, and we can take the power supply from here, because this is a main input power, and main fuses is given there. If any fuel valve like a feeder valve or any actuator valve, if you want to operate, you have to take the powers from this source only. We cannot take the power in from the A and D. And when you are changing the battery, make sure the switch is all in off position, and one more thing is there, one more dip switch is there, I will show you now. This switch is for when you are changing the MPC. If you have a trouble in MPC, number 4 switch, yellow one, put it off, then you give all the connectors, channel connections, and put the dongle here. The dongle is the ID of the unit that is fixed for each unit, we cannot be interchanged, and with that ID, this connection made, then it will get all the software, it will get automatically loaded in this VCU. After that you can reset back it, and this software is normally stored in the MOPB, and from the MOPB we are checking here. When you are starting that LED indicator having these, the boards are there, and when you are starting there is an LED indication, so indications the detail is given here. Between the frequencies 1 second, so that if one the LED is red means something error, green means it is okay, it is already loaded, and orange means it is initializing during, and then flashing one by one flash and one flash red and one flash green means like that it is given in the chart. The 2 flash and 2 in the green, then it is uploaded like that, and this is the circuit diagram for that. In EICU, what are the channels are connected, and which channel, which plug is connected to which channel, which system or sensors, it is given in the chart like that. CCU1 also I given for sample, and with that you can find out which channel is going to which sensor or valve or wherever it is going. You can easily trace out from here. And then for the reference I give some one CCU1 plug details from the channel side, and you can see that each wire number and everything is noted here, and with that we can trace the wire, which any wire is having a trouble or anything, you can easily find out, and all channels is available in the circuit diagram. It's very easy to trace out. And from here, if you want to operate any powerful valve like LV valve and all, you can do the amplifier, you can add the amplifier in between, because this same MPC power supply cannot use in the valve directly. So for that they will add the amplifier unit in between, and always they use the current 4 to 20 milliamps current to transfer the signal. That reason also I will give you in few seconds why we are using 4 to 20 milliamps. And see, the reason is that current, if you transfer the signal by current, no drop voltage, no electromagnetic interference, and if any open circuit easily can be detected, because the current minimum reading 0, and if you are showing the 0 to 20 milliamps means 0 will represent open circuit also, so it will get confused. So for that purpose we are using 4 to 20 milliamps. And also one more reason, this easily the current signal can be converted into digital voltage which easily readable by the computer. I shown you the circuit. 250 ohms they will give, so that in 4 milliamps it will give 1 volt, and 20 milliamps will give the 5 volt drop, which will easily be readable by the computer. That is why we are using this. Next one is that bus log analyzer with LVDT plot software. It is available normally in the shop. With this software only we can read this HCU events which we normally manually dump, or if any alarm comes also automatically it will dump. And this one is manual dump, we have done for demonstration. And then I open the CCU unit 1, and it will show that in what reason it is created. This is manual dump. If suppose alarm is there, it will mention here in place of manual dump. And this marker is that point where I triggered, but all the data little before the marker and then after the marker also saved, so that we can easily analyze the fault. And this 5 HCU events can store here: fever set point, fever feedback, fever control, and ME piston position and tacho angle. With this 5 we can easily find out. We can select which one you want to read a close look. We can select with that graph only, like this. And if you want to make a close view, then you can select like this square, then leave it, then you will get the zoom one. We can zoom it as much as you want. You can zoom again and again, and you can analyze the graph very close look, and then we can find the exact fault. And this is the way we are analyzing the fault. And in this, the graph horizontal line x-axis, it is time basis millisecond, and sample interval is that 500 microseconds, and vertical line is that is mm, spool valve mm, fever valve linear travel it is mentioned, and it is 2 mm into 1000 times. It is showing for easy understanding. The scale is that for 2 mm it is showing 2000, like that. And this is the place where the fever valve operated. Red one is that set point, and green one is that feedback. So we are giving an instruction this by the red point setting, and we are getting back the feedback from the spool valve, that is green. So it's only very few microseconds difference. This is the good symptom, and normally this will be there. And this blue one will be the control amps current we are giving to the fever valve, proportional current. And the light blue one is that MEP piston activated, because we have taken above the 70%, 85% load, so the MEP piston activated already. So that is showing here. Now I am going to zoom this area. Now you see how I am going. See, now I zoomed it. Now we got the 2 cycles. We will open one cycle and analysis little easily. Then now it is showing the 1 cycle, 1 revolution we can say. And you see that this the bottom line is showing that MEP piston activated, and this is the upward flank is that activation, and downward flank is that closing of the MEP piston. And that upward flank is not very much important, but the closing flank, downward flank is very important, because that is only changing the compression pressure of that unit, particular unit. And this way we can easily understand what is happening, and any error is there, easily we can compare with all units. Now I open both the units CCU1 and CCU2 is easily for comparison. This is a very useful tool for analysis in offline system, and we can take this dump from the MOP to the USB. Then this one you can see in your computer, and you can analyze this also. You can save for reference also. And this is very useful thing, and it is available. It is there in the MOP. You can easily dump it. And next one is a useful screenshot, which is I got it, is very useful to you, and you can go through one by one. You can still the picture and then you can read it what exactly given with this. The same one already I explained in the just a few minutes before, so you can go through by the words, so you can understand easily. And this is that short .3 CAM, and how we are calling, and what is the benefit of the CAM, how it is operating. You can furthermore deep understanding can do it. Now you see hydraulic HC unit, in many times we are calling it as different name, bus block, manual dump, like that. And lot of screenshot I given for your reference, which is very useful. And if you want to see it, you make a still and then you can read it. This is, you see that the fuel injection should be happen in the 0 TDC only, should not happen in the remaining area. So exhaust valve opening will be in the bottom line, and resolution also given, and feeder set point mm into 1000 they given in the x-axis. See here I shown you that ME piston upward flange is not critical, but downward flange is very much critical. That is only change the compression pressure clearance pressure ratio. So this one we have to take care of it. And I told you in the fault also the HCU event will get automatically stored. So here you can see the fault, some sample faults I gave. Here HPS problem and lot of other engine is not in the same engine, but for understanding I gave the samples how the fault will be normally, and you can get many more fault like this, but just samples only I gave just for your reference. I hope this video is very useful to you, and if any comments, please I will give that my email ID in the end of the video. Please comment to me, ask if any doubts or anything, then I will try to clarify as level my best. Thank you for watching. Welcome to GK's Tech Solution, and this video I am going to discuss about electronically controlled marine engine MEB 9.3 model, and this is also called .3 engine, developed version of MEB engines. And this is similar to MEC engine, except the exhaust valve is controlled by camshaft and with the timing unit. And this is the contents of this video. These chapters we are going to discuss detailedly in one by one. Next is engine type designation. This slide I am giving for your reference, and the details is given about the letters in the model designation. And ours is MEB, that is exhaust valve controlled by camshaft. Next is engine control system. This slide shows the actual setup of MEB engines, and each unit is controlled by cylinder control unit, which will give the exact timing of fuel injection and exhaust valve operations, which will get the feedback from the engine RPM through crank angle encoder, and also the actual position of the crank, so that can easily achieve the timing of fuel injections. And all the cylinder control unit is connected through network to the main operating panel, through which human can enter the reading and can read the actual values, and easily can troubleshoot also we can do with that. And there is a two MOP main operating panels are there for redundancy, and MOP B is actually having the troubleshooting facility to through that we can troubleshoot online only. And PME computer engine diagram system also there through hub, it is connected with MOP, so that we can performance we can check, and auto tuning also we can do it. Auto tuning means we can all the units getting balanced with automatically, and this we will discuss about later detailing. And one more unit is there, EICU, which is actually getting interface with the telegraph units from the bridge and ECR panel, and also that the EICU controls the HPS pumps. High pressure pump is required for MEB engine. For controlling that also it is done by EICU. And engine side control also there, it is all communicated with all cylinder control unit. In emergency we can operate from this engine control side. And this cylinder control unit also controls the alpha lubricator to the units for cylinder lubrication. And all cylinder pressures are measured with sensors fed to MOP-B through data acquisition unit. And from the MOP you can compare and check the pressures and tidings of the fuel injections and the pressures values, and then this data will goes to PMA computer through hub. This is the setup. And portable measuring instrument also can be used through PMI data acquisition unit for calibration purpose. And this is the setup, and we will discuss about one by one section detailing now. Next is high pressure system. Actually MEB engine concept is use of mechanical hydraulic system for actuation of fuel injection pumps, which are electronically controlled by a computer based control system. And for that main system lube oil is used as a hydraulic medium. This oil is further fine filtered by the auto filter unit and then pressurized by two electrically driven pumps to 300 bar. And for this accumulator block also we are using to get the stable oil supply to the hydraulic control units where the fuel pumps, injection pumps are fitted. And this is the setup. And after hydraulic control unit, the oil is returned back to the pump suction. And this pressure is controlled by proportional controlled pressure regulator and by EICU, as already we saw that. And this is the setup. Next is crank angle encoder, which is very important for electronic engines, which will give the actual RPM and actual crank angle position to achieve the proper timing of fuel injection and exhaust valve operation, cylinder lubrication, etc. And this will achieved by these encoders. And one encoder as a reference encoder we are going to use later. And this encoder is fitted behind the flywheel, and this will sense the position of the flywheel by sensing the semicircular ring. Semicircular ring, it is fitted behind the flywheel. You can see that blue color ring, and this ring is fitted 90-degree offset from number 1 unit TDC. This we will discuss about later. And the next setup is that hydraulic control unit for 2 cylinders, 1 hydraulic control unit which will accommodate 2 fuel pumps and the electronic fuel injection valves plus cylinder lubrication. This is the high pressure pumps fitted, and all the high pressure pipes will be fitted inside the crankcase for safety reasons. So nothing high pressure pipe will be outside. That is very important. And this is the accumulator for giving the stable hydraulic supply. And this is another two encoders. This is the main encoders. It's fitted forward of the engine. There is two they are given for redundancy, and the behind one is that first one is that encoder A, and second one, outer one, is called as encoder B. And encoder A is exactly fitted on number 1 TDC. The reference, it will take the reference from number 1 TDC, and second one 45-degree offset from the number 1 TDC. They fitted in that way, and in few minutes I will explain you why this offset is required, and this is the setup they given. And next, from this encoder the signals will go to this amplifiers, this encoder amplifier. From here, this is the actual setup, actual photo of the main engine. And now I will tell you how the encoder is working. It is just like a disc. It is rotating along with the shaft, and this setup is having infrared lights in one side, and the disc is having windows, having a transparent windows. Through that the lights are passing, and then the sensors is receiving the lights, and this will give the signal to the amplifiers. So from that you can measure the RPM and crank angle also, and we will discuss about this detailedly, how we are achieving the RPM plus crank angle with the sensor. And this is the setup, and with this small animation I will explain the working principle of these three encoder together. And there are two encoder in the forward shaft, you can see, and blue one is that encoder A. There is a main encoder, it fitted exactly with the number 1 TDC. And this is the encoder B. It is 45-degree offset from the number 1 TDC they fitted. And the third one is that flywheel encoder. It is you can see the marker, that of semicircular ring fitted 90-degree offset. Now you can see that on rotation how the thing is going on, and it is having so many sensors, not only marker sensor, it is having a quadrature sensor also. And in few seconds we will discuss about these sensors, what is the difference and why it is required this many sensors for one encoder. And you can see that one encoder, it is having 4 sensors. So what is the purpose of 4 sensors? In a few minutes we will discuss about that. And now one by one we will go with this small animations. And now you can see that we have this many sensors. That main sensor, big one, is that marker sensors, and 2 marker sensor in one encoder, which will be 90-degree offset, and small sensor together fitted, it is called quadrature sensor. That is for calculating the RPM as well as the direction of the shaft. And this is the setup. For easy understanding, I removed the crankshaft, and then I am showing what we are doing. And now what I am going to do, all the sensors, markers, I am going to turn in one direction, bring it in one position like this, so that easy for us to understand the position, what is happening, and which sensor is giving in signal, and with that what we can understand. See, this is the normal drawing normally available in the manual, and you can see that 45-degree offset the encoder B is set it. Now I will explain about this incremental encoder. This is the basic type, which is having only one sensor on the wheel, and with that sensor we are getting the signal like a graph as shown in the down below. And with this graph we can measure the RPM, only RPM, not the direction of the wheel as well as the crank angle position. So with that we can achieve this much only. For getting the direction, we need the next encoder called quadrature encoder, which is having 2 sensors together like as shown in the figure. And because of these 2 sensors together, we are getting two graphs signal outputs like below, and you can see that number 1 A sensor is leading than number 2 sensor. So with which is leading, according to that we can find the rotation of the wheel. That is the idea of this sensor, and with the timing also we can measure how much angle it is rotated. That is also is possible with this quadrature sensor. And the next one is that absolute encoder, which will give the exact crank angle also. And here the marker sensor, it is additional sensor fitted with the marker ring, circular ring on number 1 TDC. So whenever the marker ring crossed the marker sensor, it will give the starting point of the crank. From that we can get all the angles by the measurement as shown in the slide. From this we are achieving the crank angle position also. Next we will discuss about why the marker ring they given 180 degree and also 45 degree, 90 degree offset from number 1 TDC. The reason behind is that when the switch on the power after power shutdown or anything, then the system should understand which angle position currently the engine is there to achieve the starting position for the electronically system. So for achieving that we are giving this 45 degree. This animation will show you in each position the status of all 4 sensors in the tabular column. With this we can achieve which 45 degree actually the engine is now it is there, so that unit starting valve will start for initial movement. If one revolution we achieved, then all system will get resetted with that actual position. So after that the computer will calculated the correct angle, and all the system will continue to run. In this system, instead of sensor MSA in the encoder A, there are a flywheel sensor used as a reference sensor. The reason behind this, there is a chance of error in encoder A and encoder B sensors getting slipped from the shaft. So but flywheel sensor is a fixed one, will not get error anytime. So we are using this sensor as a reference sensor to calibrate the other sensors. This is the reason they given the flywheel sensor. I hope you understand all the features about this encoder, how it is working, and how much useful for finding exact position. Next is that fuel oil pressure booster, which is actually fitted on hydraulic cylinder unit. From the LFE valve, the hydraulic cylinder unit getting a high pressure oil flow. This oil flow pushes the hydraulic piston up, and this hydraulic piston will pushes the fuel oil plunger, which is in the upper position as shown in the figure, and one umbrella is given for protection of spillage, any mixing of fuel oil in the hydraulic system. And the fuel oil will go in through this non-return valve, and it by the injection happen, then the fuel oil will inject through the high pressure pipe and the fuel valves. After injection over, the piston will return back, hydraulic plunger will return back, so that that is happened by the fuel oil pressure is pushing down. This there is no spring in that, and hydraulic accumulator fitted to get stable hydraulic supply all the time. Next is that electronic fuel injection valve named as LFE or FIVA valve. It is a proportional control valve, solenoid valve, which acts as a pilot valve for the main spool valve, and this is will controlled by the PCB, which is a computer processor, which will activate the voice control drive, which which will move the spool of the pilot valve, and end of the pilot valve having the self-centering spring which fails safe. Whenever the power switched off, then this will become in the center, and this pilot valve will fitted on the main spool valve, which is actually allow the high pressure oil to the fuel oil pressure booster. And this is the actual setup. Pilot valve is fitted on the main spool valve, and in the end of the main spool valve you can see that LVDT sensor is there for finding the position of the spool, actual position of the spool, and it is the feedback, it is again passed to the LV valve PCB, which it will compare, and if any error is there, then it will cut off the unit. And now I will show you that the mechanism with a small animation, how the spool valves are working. And now in this picture you can see that LV valve is operated by voice coil drive. Through that we can move the spool, pilot spool, and pilot spool will allow the high pressure oil to the main spool, and main spool will move move up and down, so that we will get the passage of oil flow to the high pressure booster. And for a feedback sensor they give an LVDT sensor for the main spool, and FIVA valve also having a sensor is a pink color, you can see that one near the voice coil drive. And in few seconds I will explain how the voice coil drive is working. And this self-centering spring, it is for fail safe. In any power failure happen, then the pilot valve spool will become in center position, and the main spool valve will be in the same position without